Okay, welcome to Lecture 40. This is 9.5. We're covering kinetic molecular theory. Kinetic molecular theory is something we use to explain gas behavior. It's what we use to explain the gas laws. Remember, theory is higher than, it's better than laws. So this is the explanation that comes in and covers why all the laws do what they do. So, talking about gases, KMT tells us that gases are composed of many tiny particles. Now that should come as no surprise. In constant motion. And they never stop moving. And they're moving in straight lines. Okay, so they only change direction when they collide, either with one another or with a wall. Okay, so a particle can run into another particle, and that will cause them both to change direction, or the particle can run into the wall of its container, and thus causing only itself to change direction. So there's no curving, there's no swooping. It's just very, very simple, lots and lots of straight lines, interrupted only by collisions. So lines and corners, corners and lines. No curves. Okay, next up, individual particles have zero volume. Okay. Technically, what the law says is that they have negligible volume compared to the space in between the particles. Okay. The particles are so very, very small that they don't take up any volume at all. It's just the sort of a simplifying assumption going into this. KMT is all about ideal behavior rather than real behavior. So this is kind of a fudge, okay, because the individual gas particles, yes, obviously they do have volume. They do take up space. But for a lot of gases, the individual particles are incredibly ridiculously tiny compared to the amount of space in between them. Okay. So what this allows us to do is sort of ignore the particles themselves while taking them into account. Because we can just say the total volume available is the total volume of the container. We don't have to worry about the space occupied by the other particles. Okay. So that can have a lot of significance. Let me clean this up. But for KMT, when talking about ideal gases, this works quite well. We'll talk about the conditions when that's no longer the case later. We'll talk about that later. Okay, so pressure equals collisions of particles with walls. Okay, so remember, pressure is force over area. The area is the walls of the container, and the force is the collision of the gas particles with the wall. Okay, so each time a particle runs into the wall of a container, it's bam, this teeny tiny little bit of force. But you have a skajillion gas molecules, particles, what have you. That's a lot of collisions, and they add up to a significant amount of force. You divide that by the wall of the container, the area of the container, and you get the pressure exerted by the gas. Okay, so all pressure, all gas pressure, is just jillions and jillions of collisions, imparting small amounts of force, one bam, bam, bam after another. Okay, next up, particles don't interact except to collide. Okay. What this is saying is that they don't exert attractive or repulsive forces on one another. Okay, so it's just another simplifying factor. Okay, so the two simplifying factors we've had so far, this one and this one, just saying that all they do is they move in a straight line until they collide, and that's it. Okay. And this is another simplifying assumption that often it often works, it's often good enough, but there are scenarios in which it is no longer the case, okay, where you can no longer make this assumption, where the particles do have significant interactions. And obviously they have significant interactions. That's why they become liquids and solids, okay, is because they do have those forces. But a lot of the time you can just sort of ignore those forces because those forces have been overcome. They're in a gas state, so they are minimal enough that they no longer count. They no longer matter. And finally, part of the definition of temperature is that the average kinetic energy of your particles is proportional to temperature. Temperature is a measure of the average kinetic energy of the particles of your gas. Okay? So the higher the temperature of an object, the faster the random motions of the particles in the object are. And this is true for solid or liquid or gas. All matter. The particles are always in constant motion. It's just that that motion is a lot more significant for a gas than it is for a liquid or a solid. Nevertheless, it does play a role. And just average kinetic energy is just one of the definitions of temperature, but it plays an important role, and we have to throw it in specifically into KMT. So now let's start using this newer and more physical understanding of particles and gas behavior to try and understand the gas laws. Okay, let's start with Amonton, pressure versus temperature. P1 over T1 equals P2 over T2. Okay, remember, for this one, N and V are constant. Okay, so we're in a sealed container with a particular number of particles. Okay. Why does changing the temperature of your gas change the pressure of the gas? Okay, let's talk about increasing temperature. Well, what happens when you increase temperature? You're increasing the kinetic energy of your particles. Okay, so you're increasing kinetic energy. Okay, kinetic energy, the energy of motion, they're moving faster. Okay, so you get faster particles. So increasing temperature means faster particles. Faster particles means harder collisions. So you're still getting the same number of collisions, right? But they're hitting harder. Same number of particles, same volume of your container, but harder collisions. So bam, bam, bam. Pressure is equal to force over area. You're increasing the force when you increase the temperature. So that's how KMT can help us understand these laws, just by putting everything in terms of the actual physical actions of particles. Okay? So increasing temperature increases velocity, increases the speed of your particles. That's going to increase the force of those collisions. That's why pressure goes up. Similarly, decreasing temperature causes the particles to go slower. That decreases that force, decreases your pressure. Okay, so now let's look at Charles's law. V1 over T1 equals V2 over T2. Moles and pressure are constant. Okay, but volume is not. So we're looking at a cylinder with weights on it to maintain constant pressure. But the volume of your system can change. That piston can move up and down. So because moles is constant, you can think of that as being number of collisions is constant. So what happens when you increase temperature? Well, once again, increasing temperature leads to increasing the force of those collisions. This is a slightly more complex scenario. So let's look very closely at that piston head. Okay, so you have your gas inside, you have your air outside. And let's just go ahead and say you have a force inside. or on the outside holding the piston down. And you have the gas exerting pressure, a force on the inside. When you increase the temperature, you increase the force inside. In, not out. Okay. So this arrow gets bigger. So what's going to happen is you're going to push the piston up. Okay. And as that happens, you're going to increase the volume inside the cylinder. So there are two ways you can think about this. But let's go ahead and just think about it in terms of the purely physical one. Okay. You started out down here. Now you've moved your piston up to here. Okay. You start out at the dotted line down here. You move up to where the piston is now. You've increased the volume of your container. So that means you've got all this wall that was available before and is not. Okay. So in terms of the math, P equals F over A, you've increased the area. You increase the force, you increase the area. Eventually, those increases will balance out. Pressure remains constant. But in terms of what's actually physically happening, okay, the number of collisions is remaining constant, okay, because you have the same number of moles. So when you increase the amount of wall space, okay, you've increased the force, and now you've increased, by increasing the volume, you're increasing where they can run into. Okay. At the smaller volume, there was some chance, X%, that they would run into the piston head. Okay. At the larger volume, there's a lower chance that they'll run into the piston head just because you have more stuff, more wall for them to run into. Okay. So there's fewer collisions against the head of the cylinder. That's why increasing area decreases pressure here. So you have those two different ways of thinking about it. Just in terms of the math, first you increase the force, the piston head moves out, which increases the area. So first you increase the force, second you increase the area, until, the pressures inside and outside are equal. Okay. You can also think of it in terms of just where the gas particles can collide. The further out the cylinder head is, the further out the piston goes, the more wall there is for the gas to run into. So the less often the gas runs into that cylinder and runs into the piston. And eventually, the forces inside and outside will be equal again. And the exact same thing happens in reverse when you decrease the temperature. You decrease the temperature, you weaken the force of the collisions, so you're decreasing the pressure inside the container. The piston head will fall down, decreasing the amount of wall space available, which means that the gas particles are more likely to run into the piston head until the forces are equal again, until the pressures, I should say, are equal again. Okay. So that is how KMT explains this particular law. So I know that one was a little bit complicated, but they can't all be easy. Next up, Boyle's law. P1 V1 equals P2 V2. So N and T, moles and temperature, are constant. So why does changing volume change pressure? Why does changing pressure change volume? Okay. Once again, we have a container where the volume can change. So why does squeezing on that container, why does increasing the pressure, by putting weight on it, say, cause the volume to decrease? Well, we already discussed a good portion of that. You have all these collisions, on the inside of the container. Some percentage of them are against the piston head. So as you put more pressure on there, the piston head starts to move down, okay, decreasing the total area available, while leaving the area of the piston head the same. So increasing the number of collisions against the head of that piston, increasing the force specifically against the piston head. Okay. Or just to put it in the mathematical terms, P equals F over A. You have to change the area. You can't change the temperature. You can't change the force. Force is going to be constant in this one because N and T are constant. Okay. So it's just the area. The area is the only thing that can respond. So you increase the pressure outside, you have to increase the pressure inside until they're equal. The only way you can do that is by decreasing the area of the walls of the container. So for P to increase, A has to decrease. So whichever way is better for you to think about this, in terms of the actions of the individual particles, in terms of the math formula, in terms of something else entirely, I don't particularly care. So long as you can find some way to connect kinetic molecular theory with the laws, to explain them. And now Avogadro's law, V1 over N1 equals V2 over N2. Okay. Why does increasing moles increase the volume? Well, this is kind of a duh, but you might as well get to it. So pressure and temperature are constant for this one. So once again, we have a container that can change the number of, or can change the volume, and you have some way to put more gas in or let some gas out. Okay. So what happens when you put more gas in? Well, you're going to get more collisions. So you're not changing the force of the individual collisions. Temperature is constant, so you're not changing the force of the individual collisions, but you are increasing the total number of collisions. So more collisions means more force. Okay, so pressure, temporarily increases, but the cylinder moves out because pressure has to stay constant for this one. So the pressure outside isn't changing. So the cylinder, the piston moves up, the volume increases, area increases. Oops. Until, the pressures, so that the pressures remain equal the whole time, really. Okay. So that's why, for Avogadro's law, okay, pressure and temperature have to remain constant. So when you put in more moles of gas, you're going to get an increase in volume, so that the increase in force due to the increased number of collisions is going to be matched by an increase in area. Okay, so more moles means you need more volume to accommodate them. And finally, the law of partial pressures. Can KMT, can kinetic molecular theory, help us understand the law of partial pressures? Well, yeah. Remember, the law of partial pressures is the total pressure is just equal to the sum of the individual pressures. Okay? That's because, remember, the particles don't interact in kinetic molecular theory except to collide with one another. So if you have, a mole of A and a mole of B, okay, so 1 mole A plus 1 mole B, the particles of A and the particles of B don't care that the other particles are even really there, okay, because they're not interacting except to collide. There's no attractive or repulsive forces. So according to KMT, there's just really no difference between A and B. So you could just as easily have 2 moles of A or 2 moles of B, and it would all be exactly the same. Okay, so that's why the law of partial pressures works the way it does. What moles you have are less important than the total number of moles you have. So now let's work our way toward understanding diffusion and effusion in terms of kinetic molecular theory. First, we're going to have to take a slight detour to kinetic energy. Kinetic energy is 1/2 mu squared. This is a slightly different formulation because we're talking about a whole lot of particles moving randomly in all sorts of different directions, rather than a single object moving in one direction. So for the single object moving in one direction, it was 1/2 mv squared. Okay. So we change it to U, and we change it from mass to molar mass. Okay. Molar mass just because moles of particles. Okay. And U because we're talking about particles moving in random directions. We have to look at a sort of average. Let's scribble that out. I don't want you confused. We're looking at a sort of average called the root mean square. Because the particles are moving in all directions, if you were to try and take a simple average, it would just be 0. They're moving in all directions equally. So you take the root mean square so that you can ignore what direction they're heading and just focus on how fast they're moving. Okay. And so that's why we take the root mean square velocity. So it's a slightly different formulation. Not excessively important, but it does give us interesting results. When we actually look at our gases, what we find is that kinetic energy is equal to 3/2 RT. Okay, so kinetic energy is directly proportional to temperature, and the proportionality is 3/2 R. It's just based right there in the universal gas laws, or in the universal gas constant. Okay, so then that gives us is equal to 1/2 mu squared. So now let's go ahead and solve for U. Not you, the listener, U as in root mean square velocity. So you multiply both sides by 2, and you rearrange a bit. You're going to get U squared equals 3RT over M. So then you take the square root of both sides. U is equal to the square root of 3RT over M. So the first thing I want you to take away from this is that higher temperature equals faster particles. Okay. Not directly. It's a square root relationship. So you have to get the temperature 4 times higher to get the particles twice as fast, but it's still an important relationship. It's a significant relationship. Higher temperature, faster particles. The other thing is that molar mass plays a role. High molar mass equals slow particles. Okay. So we're already well on our way to understanding F-fusion and diffusion, because you see that square root. I told you it would come up eventually. Okay. Hey! So now we can compare two gases by saying you have U1, so the speed of particle or gas 1 is equal to square root of 3RT over M1. And for gas 2, square root of 3RT over M2. Okay. And now we can compare how fast they're moving, which is going to be directly related to F-fusion and diffusion, because how fast it diffuses and diffuses is just how fast the particles are moving. So U2 over U1 is equal to square root of 3RT over M2 divided by the square root of 3RT over M1. The 3RTs cancel out, and then you're going to get a sort of flip-flop, because 1 over A over B is equal to 1 over AB. A over 1 over B is equal to just AB. So that's why the M1s and M2 here, they switch sides, and you get M1 over M2. That's why you get that reversal in the rates for effusion and diffusion. So a heavier thing will effuse or diffuse slower than a light thing. And it goes with the square root just because kinetic energy is 1/2 mv squared. So that is where that law came from for effusion and diffusion. And it's a little bit harder to see, but it also comes directly out of KMT. That whole kinetic energy equals 1/2 mu squared was from kinetic molecular theory. The fact that it was equal to 3 RT, 3 halves RT, is likewise also from kinetic molecular theory. I didn't show you those derivations just because those are even more unpleasant than the algebra we've had to cover so far. And that is it for 9.5. I'll see you in the next video.